This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Let's model the series circuit as follows. Let's say the source has 2 ohms of internal resistance, as does a non-ideal ammeter. We'll additionally make use of 2 voltmeters, each with 20 kiloohms of resistance, in parallel to R1 and in parallel to R2. You will note that in accounting for these non-ideal elements, we are no longer dealing with a pure series nor a pure parallel circuit, but rather a much more complicated series parallel circuit. As an exercise to the viewer, I invite you to determine the voltage across and the current through each resistor in this system, as well as source current. This will be a lot harder than previously. Again, we're only looking for V1, V2, I1, I2, and source current for each system. By all means, pause the lecture and try this by yourself. If you're tracking, you should have obtained the following values. The parallel combination of R1 and the non-ideal voltmeter 1 presents a resistance of approximately 119.3 ohms. Similarly, the parallel combination of R2 and non-ideal voltmeter 2 presents a resistance of roughly 582.5 ohms. The internal resistance, the ammeter, R single prime and R double prime are perfectly in series with one another. An application of the voltage divider rule to the pure series simplification demonstrates the voltage across the ammeter is 102 millivolts. An application of Ohm's law demonstrates the ammeter experiences 51 milliamperes. Ostensibly, this is the source current for this system. Another application of the voltage divider rule demonstrates that V single prime is 6.1 volts. Another application of the voltage divider rule demonstrates that V double prime is the remaining 29.7 volts. Voltage across elements in parallel is the same. V single prime equals V1, which equals V voltmeter 1, and they all equal 6.1 volts. An application of Ohm's law demonstrates that I1 is 50.7 milliamperes, and another application of Ohm's law demonstrates 304.2 microamperes is routed around I1 through the non-ideal voltmeter. Again, voltage across elements in parallel is the same. V double prime equals V2, which equals the voltage across the non-ideal voltmeter 2, and they all equal 29.7 volts. An application of Ohm's law demonstrates that I2 is 49.5 milliamperes, and another application of Ohm's law demonstrates that 1.5 milliamperes is routed around R2 through the non-ideal voltmeter 2. Ultimately, accounting for these non-ideal effects, the ammeter measuring source current displays 51 milliamperes. However, because of the leakage paths presented by voltmeter 1 and 2, R1 experiences only 50.7 milliamperes, and R2 experiences 49.5 milliamperes. Voltmeter 1 reads 6.1 volts, and voltmeter 2 reads 29.7 volts. When we compare these results with our initial idealized calculations, there's a small but noticeable difference. An observer ignorant of non-ideal sources and instrument loading effects may suspect minor violation of fundamental series properties. However, a savvy aspiring technician, such as yourself, is keenly aware of the more complicated series parallel circuit underlying reality and can account for and explain these differences. Let's now take a look at the non-ideal parallel circuit. If you recall, the original circuit was a 16-volt source in parallel with a 480 ohm resistor and a 240 ohm resistor. Let's include 2 ohms of internal resistance in the source, a non-ideal ammeter used to measure source current, which happens to have an internal resistance of 2 ohms, another non-ideal ammeter used to measure current through resistor 1 that also happens to have an internal resistance of 2 ohms, and finally the third non-ideal ammeter used to measure current through resistor 2 that also happens to have an internal resistance of 2 ohms. Finally, we include a non-ideal voltmeter that happens to have an internal resistance of 20 kiloohms in parallel with R2. As an exercise to the viewer, I invite you to determine the voltage across and the current through each resistor in this system, as well as source current. This would be much more difficult because it takes several levels of simplification to bring it down to a pure series circuit. Stay organized. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. Here's how I solve for these values. The series combination of the non-ideal ammeter and R1 presents a resistance of 485 ohms, a simplification I'm calling R single prime. The parallel combination of R2 and the non-ideal voltmeter presents a resistance of roughly 237.2 ohms. Let's call this simplification R double prime. The series combination of R double prime and the non-ideal ammeter used to measure current through resistor 2 presents a resistance of roughly 242.2 ohms. Let's call this simplification R triple prime. Finally, the parallel combination of R single prime and R triple prime presents a resistance of roughly 161.5 ohms. Let's call this simplification R quadruple prime. R quadruple prime is perfectly in series with a non-ideal ammeter used to measure source current and the internal resistance. Using the pure series simplification, an application of the voltage divider rule demonstrates the voltage across the ammeter used to measure source current is 193.3 millivolts. An application of Ohm's law demonstrates the ammeter used to measure source current experiences 96.7 milliamperes. Ostensibly, this is the source current for the system. Another application of Ohm's law demonstrates that V quadruple prime is 15.6 volts. R triple prime is the parallel combination of R single prime and R triple prime. Voltage across elements in parallel is the same. V quadruple prime equals V single prime, which equals V triple prime, and they all equal 15.6 volts. An application of Ohm's law demonstrates that I single prime is 32.2 milliamperes. I single prime is a series combination of non-ideal ammeter 1 and R1. Current through elements in series is the same. I single prime equals I ammeter 1, which equals I1, and they all equal 32.2 milliamperes. An application of Ohm's law demonstrates that V1 equals 15.5 volts. Now let's examine the parallel path on the right. An application of Ohm's law demonstrates that I triple prime is 64.5 milliamperes. R triple prime is the series combination of the non-ideal ammeter used to measure current through R2 and R double prime. Current through elements in series is the same. I triple prime equals I ammeter 2, which equals I double prime, and they all equal 64.5 milliamperes. An application of Ohm's law demonstrates that V double prime is equal to 15.3 volts. R double prime is a parallel combination of R2 and the non-ideal voltmeter. Voltage across elements in parallel is the same. V double prime equals V2, which equals the voltage across the voltmeter, and they all equal 15.3 volts. An application of Ohm's law demonstrates that I2 is 63.7 milliamperes. Yet another application of Ohm's law demonstrates 764.5 microamps leaks around resistor R2 through the non-ideal voltmeter. Ultimately, accounting for these non-ideal effects, the ammeter measuring source current displays 96.7 milliamperes. The ammeter measuring I1 displays 32.2 milliamperes, and the ammeter measuring I2 displays 64.5 milliamperes. This being said, because of the leakage path presented by the voltmeter, R2 in reality experiences only 63.7 milliamperes. Similarly, the voltmeter measuring voltage across R2 reads 15.3 volts. However, R1 really experiences 15.5 volts. As previously, when we compare these results with our initial idealized calculations, there's a small but noticeable difference. An observer ignorant of non-ideal sources and instrument loading effects may suspect minor violations of fundamental parallel properties. However, a savvy aspiring technician, such as yourself, is keenly aware of these more complicated series parallel circuit underlying reality and can account for and explain these differences. As these example problems were intended to illustrate, accounting for the non-ideal nature of sources and instrumentation, one might expect to witness small variations between calculations and real-world observations. This being said, even for such inflated non-ideal effects, the variances aren't all that bad. On a more devious level, this discussion on instrumentation loading effects served as an excellent means of tricking you into more practice and exposure with series parallel circuit analysis. If you perform these analyses correctly, especially that last circuit, you'll most likely do just fine. If not, don't worry, there will be a lot more opportunities for practice in the very near future. In conclusion, this lecture took an introductory look at instrument loading effects and discussed how the act of measuring an electrical quantity can influence the circuit's behavior. You will be overjoyed to realize that a well-constructed ammeter or voltmeter will not unduly or excessively influence the circuit's behavior, and any effects can be considered negligible for our purposes. This discussion, however, presented us with the opportunity to employ our series parallel circuit analysis skills on increasingly complex circuits. You should have an appreciation for the complexity behind the simplifications employed in circuit analysis, and you should be able to account for minute differences observed in the course of study using previously acquired circuit analysis skills. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.